begin with. Something's funny.
Oh no, everyone's commenting on my food. So
Your what?
my food.
It's made of real vegans.
Well, enjoy it. Oh shit. All right, so let's see. I just wanted to. We were talking about. You've got the thing on, right?
Yeah.
So we were talking about scalar, QED, or and in fact, instead of saying scalar electrons, we can call them selectrons, which is the supersymmetry term. There was one. We were examining we were translating basically the vertices into numbers, formulas, and what we hadn't done was the last vertex, the one that comes from the term, from this term, and if we rewrite this e squared a to mu nu a mu a nu phi star phi, then you can see that this would give us diagrams like, well, in the book there's only one diagram, but in fact this term actually gives us 4 diagrams. So one is an electron scattering off a photon, or a selectron scattering off a photon. But there are 2 more diagrams. There is hold it. I wrote that incorrectly. I got this eraser wet. It works okay. All right. Here is a positron. Almost sounds like suppository. But anyway, a positron scattering off a photon. And then there are 2 more. There is selectron, positron annihilation into 2 photons. And then finally, there's 2 photons going to electron-positron pair. So this vertex actually, or this formula in the interaction with Röntgen gives us 4 different diagrams. All right, now we need to deal with the initial states and final states, and so let me just remind you how that will go. First of all, for the phi field, phi of x, of course, is an integral d cubed p over 2 pi cubed a sub p is minus I px plus a dagger of p I px. And these are Lorentz products, and we divide by the square root of 2 omega p. Consequently, phi star is the same thing almost. It's the adjoint, so it's AP dagger e to the plus IPX plus, whoops, this is a B, plus BP e to the minus IPX over square root of 2 omega p. Okay, so this is the field, and it's adjoint. Is there a question? No. Now, an initial selectron state would be K, and in Schwarz's normalization, this is 2 omega K, AK dagger on the vacuum of the free theory. Actually, I turned these on, let me turn them off. The reason I opened the window and the door is that there was an exam in here, and there were lots of students. The place smelled like an armpit. So that's why I opened the door and the window. The creation part of phi, or the annihilation part of phi, that acting on this state k, then is an integral cos d cubed p 2 pi cubed, and it would be effectively a commutator. It would be this thing here, e to the minus I px, and then it would be ak dagger commutator square root 2 omega k vacuum divided by square root 2 omega p. And the commutator of AP with AK dagger is in Schwarz's normalization 2 pi cubed over cubed of P minus K. Okay, so this thing gives you a 2 pi cubed cancels that. The omegas cancel because when P equals K, the omegas are the same, and then you have a delta function which allows you to do the integral painlessly. And the answer is simply e to the minus I kx vacuum. And similarly, just by taking the adjoint, the final state particle with a creation part of this electron field is e to the I kx vacuum. So that's how that looks. That's how we deal with final states for the electrons. Now, on the other hand, the electromagnetic field is a little bit more elaborate. It's a mu of x is an integral d cubed k 2 pi cubed. And now we've got 1 over square root of 2 omega k, so that's just for this electron. But now we have to sum over the two polarizations, and then we have epsilon mu I of k, ak I. And this I is just goes from 1 to 2, so there's no significance to it being raised. And e to the minus I kx plus epsilon mu I star of k, ai dagger k, e to the I kx. Okay, so that's the other. So that's our electromagnetic field. And now, if we have an incoming photon of polarization p, I'm sorry, momentum p, polarization j, then a mu of x on that, and I might as well take the negative frequency part of that. That is a minus mu of x on square root of 2 omega p, ai dagger of p on the vacuum. And you can see that it parallels the argument here. The only difference is we have an extra polarization here. And so what we get is epsilon j mu of p e to the minus I px vacuum. So it's the same as this. The only difference is that you get a polarization index, the polarization vector, and you get the muth component of the jth polarization vectors, and only 2 polarization vectors. Okay, any questions? Yes, thank you for the question. Let me reward you with some junk food.
So wait, I don't get where the J comes from in this polarization thing. That's so.
It was, well, you've got.
You get a Kronecker delta from that, or
well, I mean, yes. If we're talking about the AKI APJ is 2 pi cubed. So it's just like this, 2 pi cubed yes, Jeanette. I mean, middle of class, dear.
Okay, bye.
Bye. She only calls me during class. The rest of the time, she ignores me. And then it will be, as you point out, delta ij.
Right.
So polarization is the same, and they're just two polarizations. And I think the way to think of them is left and right circular polarization. This linear stuff is. Linear just means you're a certain linear combination of the two circuits. All right. The next thing I want to do is compute a certain, how shall I say, a certain amplitude in a certain amplitude for scattering. Now, Schwartz does it by simply writing down the Feynman diagram, and that's okay, but it seems to me that it would be good for me to show you how you actually get this formula from the fundamental formula of scattering. So I'm going to do this in much more detail than in the Schwartz book. And the amplitude here is a photon of momentum P1 coming in, and we can put an arrow on it if we want. P2 comes in like this. This is an electron. K is here. A selectron goes out, and a photon goes out. So this is the picture. And the relevant part of the interaction Lagrangian is just the part that gives us these two vertices. And that part is IL interaction is ... plus E a mu phi star d mu phi minus phi d mu phi star. So that's the term that is going to contribute to this process, and it's going to be contributing twice. And so what I'm going to compute is the S matrix element, and so I'm going to be talking about, in other words, P4 epsilon 4 P3. This is the final photon, the final selectron. And then what we have here is time-ordered product, e to the I integral Li d4 x. And then the initial state is P1 epsilon 1 P2. So I'm going to compute this, cost of lowest order. And the first term is 1, and that's going to vanish because the initial and final states are different. The second term is also going to vanish because we would just have, actually, the first order term, now that I think about it, doesn't, for this process, if we're talking this process as opposed to this diagram, for this process, this term contributes. In other words, it would be this diagram right here. But Schwartz doesn't talk about this, so I'm going to instead look at the second order term. So so let me put in, just while I'm at it, I should just add that
plus I e squared a mu phi squared. This is also contributing to the process, but I'm just looking at this diagram. Yes?
What's that K in between?
What?
What's that K?
Oh, the K, well, K is going to be clearly P1 plus P2.
Is that a
Because
photon?
momentum is conserved at every vertex in every Feynman diagram.
Is that a photon or some?
That is a selectron line. All right. Okay, so as I said, we're just looking at the second order diagram for the cubic term. And so in particular, it would be a minus 1/2. Actually, now that I think about it, I see that I left that minus sign. Oh no, I didn't leave that minus sign out because I'm taking IL to be this, so this is plus 1/2. And then it will be P4 epsilon for P3, time ordered product, and now an integral d4th x, d4th y, and now this particular thing here, which is e squared a mu phi star d mu phi minus phi d mu phi star, all that at x times the same thing. Actually, it's not e squared, it's just e a nu phi star d nu phi minus phi d nu phi star. And then finally the initial state, which is P1 epsilon 1 P2. Okay. So I'm going to work this out for you in detail. Now, the first thing to notice, in fact, I like to think about this calculation in, I mean, it starts out in position space, doesn't it? Because it's d4th x, d4th y, li of x, li of y. So we're in position space, but we can use the same Feynman diagram. And now, you see there are two equivalent cases. You can imagine that this vertex is x, and that one is y. Or you can say, well, no, this one was actually y, and this one is x. Okay? But of course, it doesn't make any difference. And so that's how the factor of 2 is canceled. And that's a factor that typically cancels in Feynman diagrams. Certainly it always cancels in diagrams like this. So what I'm going to do is I'm going to say this is x, and that's y when I evaluate it. And that's why I can cancel the 1/2. So the next step then is that the point x, which is this one here, this thing is going to stop selectron with momentum P2. And so we get rid of the 2 of the 1/2, we cancel that. And what does that look like? Well, it's an annihilation part of the field phi on a state, and that just gives us a phase factor. So this thing is going to be, and I'm going to call this, I'm going to call it Im prime, and I'm putting a prime on it because I'm going to have the whole, this would be the whole S matrix element, whereas Schwartz writes down a formula for this, which is which doesn't have the overall delta function or the density of final states. So this is Im prime equals, so this is then P3, P4, E4, integral again. So I guess I might as well do it this way. D4th x, D4th y, time ordered product. Okay. And now we're going to have E a mu of x. And now this phi that can stop the incoming electron, there, if you look at it, you see it can be stopped by this field, but then there's a derivative term, or it can be stopped by that field. And then there's another derivative term. So what we get is phi star of x I p2 mu with a minus sign. And it's a minus sign because we're differentiating this term. There's a minus sign there. And then the other one is minus simply d mu phi star of x, and we get a factor e to the minus I p2x. So that's what happened there. And the rest of this is just as it was, namely e a nu phi star d nu phi minus phi d nu phi star, all at y, p1 epsilon 1, but there's no p2 anymore because that one has been eliminated. Any questions? This procedure that I'm going through is common to all of these Feynman diagrams. Anything that you evaluate, if you evaluate any of these Feynman diagrams from first principles, you go through essentially this procedure. Okay, now, the next thing we want to do is deal with the photons. Well, the photons are playing a much simpler role because there aren't any derivatives and there's only one photon field in each term. So the photons behave pretty simply. And what we have then is a minus on the initial state, and correspondingly we have P, A, J, A plus mu of x. Just taking the adjoint of that, that's epsilon J star mu of P, e to the I, Px. So we use this formula and that formula to create this photon and stop that photon. And when we do that, what we have is simply P3. Well, let's see, I keep writing without looking at my notes, and as you know, that's always a mistake. Almost. So let me pull out the epsilon 4 nu star of P4. So that's the polarization vector that occurs here for this photon. And also the polarization vector for this one. And so that one is epsilon 1 mu of P1. And now the rest of it will be d fourth x, d fourth y. We still have, well, we can pull out an e squared, which is the square of the charge, because there's one of them here and one of them there. And then we have P3, time-ordered product. And now this structure here, which is phi star of x minus I P2 mu minus d mu phi star of x. And then over here, the rest of it then is phi star of y, d nu phi of y, minus phi of y, d nu phi star of y. And we just have vacuum. And now we have phase factors. And the phase factors are e to the I P4y minus minus I P2X minus I P1X. So at X, we've absorbed the photon and this electron, and so far we've created the final photon at Y, and the only thing left is we have this final state selectron. And so if we once again use this formula and notice that this one has to occur at Y. And secondly, it's a final state electron, so it only comes from a phi star. All right. And so, in fact, when I wrote, when I was doing this for thinking in terms of a selectron, maybe I should have been a little more careful there. If we have a final state selectron, then the thing that creates a final state electron is it's phi star plus here. Because, I mean, if we just had neutral fields, then it would be just phi plus and phi minus. But if we're talking about selectrons, then the thing that annihilates an incoming selectron is phi minus, and the thing that creates an outgoing selectron is phi star plus.
I thought that was a dagger the whole time. So.
Well, you're certainly excused for thinking of it as dagger. There. So that's a dagger. It has a very short blade. It might even let you take it on a plane. Okay. So let's use phi star of Y and the plus part of it to create this final selectron. And when we've done that, we have E nu star, E nu 4 star, and I think I can just call it E nu 4, meaning it's a P4. Okay. And then we have E nu 1, and then we have E squared, and now we have an integral d4th x, d4th y. Now the phase factors are e to the iy times p3 plus p4, e to the minus ix, p1 plus p2. And what's left is vacuum time-ordered product. And now these two things are minus I p2 mu phi star of x minus d mu phi star of x. And I guess I have to put brackets around this. And then this thing, but without the phi star terms. And so what we have then is d nu phi of y minus I p3 nu. And where did this come from? This came from the d nu acting on the phi star. Okay. And the phi star of y has e to the I y p3. So it comes down with a minus sign because of that minus sign. It's all quite straightforward. It's just there's a lot of detail. And in fact, you may say, gosh, this is sort of complicated. Well, it's complicated because scalar electrodynamics is actually in some ways more complicated than ordinary electrodynamics. Because we've got, I mean, the interaction Lagrangian for ordinary electrodynamics is just E psi bar gamma mu a mu psi. So that's a lot complicated, simpler than all of this. Okay. So you have something to look forward to. Okay, anyway, minus I P3 nu phi of y, and then vacuum, and that's it. Okay. And so you might say, well, what do we have here? We have to close the time ordering. This is going to give us the propagator for the selectron. And we haven't calculated that yet, so I thought I would actually, in fact, show you in detail how to do that also. All right, so we'll start out with simply vacuum, time-ordered product, phi star of x, phi of y, vacuum. So that's what's occurring here. It's just that we have 4 terms dressed up with p's and derivatives. And we can take care of them later. Let's first look at this. Well, this, of course, is theta of x0 minus y0. So this is a review of how you get Feynman propagators. But since the Feynman propagator is so important, and it's essentially the same thing for electrons, scalar particles, photons, gravitons, it's always something or other divided by p squared minus m squared plus I epsilon. So it doesn't hurt to see this a second time. And what we've got left here is phi star minus at x, phi plus, make it legal for aircraft travel, plus theta of y0 minus x0. And now we have phi minus of y, phi star plus of x 0. Okay. All right. Now, so I'm just going to go over to this board and say that this is equal to cos theta x0 minus y0, and the first term is, of course, well, we have an integral dqp, dqp prime, we have 2 pi to the 6 square root of 2 omega p, 2 omega p prime. And then we have 0 b p, b dagger p prime, 0 e to the minus I px plus I p prime y, and then the other term is plus theta of y0 minus x0. Well, same business, so why don't I just say ditto, and the only thing that's different is 0 a of p prime, a dagger of p, 0, but now the phase factor is different, so it is e to the minus I p prime y plus I px. Okay, so that's what this selectron propagator looks like. And of course, this thing here gives us 2 pi cubed delta p minus p prime, and this does the same. And consequently, actually, maybe I should, I didn't ever derive that for you. We defined the annihilation creation operators for neutral fields originally. And so let's just see, let's just look at this one then. So we have, in fact, what I want to do is do the commutator. So let's do a p prime, a dagger p. This is a dagger, long, sharp dagger. Now what is this? This is actually 1 over root 2 a1 p prime plus I a2 p prime. That's what that is. And this one is 1 over root 2, and then it's, I'm going to do this in a clumsy way. I'm going to say this is a1p plus I a2p dagger. Long, sharp dagger. All right. And now what happens is, if you let me just bring the dagger through using the properties of the eraser, the dagger will put a dagger here, a dagger there, and it'll change the I to a minus I. So we'll get minus I, dagger, dagger. Let me get rid of this dagger. Now what we've got is A1, commutator A1, dagger, at the P prime, these are both prime. Oh no, those are both P. So that gives you 2 pi delta, 2 pi cubed delta of P minus P prime. This one, the I with the minus I, you see, gives you plus 1, 2 pi cubed delta P minus P prime. But A1 commutes with A2 dagger, and A2 commutes with A1 dagger. So we just get the same thing twice, but root 2 times root 2 is 2, so that cancels. So this is altogether just 2 pi cubed delta P minus P prime. Of course, you knew that, but I just wanted to show it to you how it happens if you think fundamentally of the fields as linear combinations of 2 real fields of the same mass, or mass 0. So once we do that, we see that this thing, what does it do? It just kicks out a 2 pi cubed, which cancels 2 pi cubed here. And then it gives us the delta of P minus P prime, which lets us do the dqp integration. And when we're done, we then have simply dqp over 2 pi cubed 2 omega p, because these guys are the same. And then we have theta of x0 minus y0. The phase factor, which is e to the ip y minus x, notice that p prime is p now, and because this p prime was on the mass shell, so if the 3 part is equal, so is the 4 part, the 4th part. And then plus theta y0 minus x0 e to the ip x minus y. So that's what we've got. The next thing we do is we flip the 3 part of the first integral. Notice, because we have Schwarz's metric, this is minus ip3 dot y minus x, the 3 part of it, the space part. And so we flip minus p y minus x to minus p x minus y, which is what occurs here. And we can do that because omega p doesn't really care. And so what we've got now is integral dqp 2 pi cubed, 2 omega p, and now e to the minus I p3 dot x minus y, which is this term here. And now we have theta of x0 minus y0 e to the I omega p x0 minus y0 from here, keeping, oh hell, I lapsed into a different metric by mistake. It's not going to matter, but I need to fix it somehow. So this is y minus x. The Schwartz metric is p0 is omega p y minus x. And so this is a minus plus theta of y0 minus x0 e, and this would be I omega p x0 minus y0. Okay, now this bracket, we're going to use equation 6.28. I'm not going to take you through the concentration again. What we can do is label, I'm beginning to think, by the way, that I flipped the wrong 3 part.
Should I flip the other one?
I should have flipped the other one, I think. Because, but it may be good for you to see that you can make an even number of mistakes. Okay, so let me see. All right, I'm going to call this tau. And then what we can say by that formula, 6.28, is that square bracket, which is that square bracket, is equal to minus 2 omega p over 2 pi I integral dp0 over p0 squared minus omega p squared plus I epsilon, and this would be e to the I omega, and in my notes it's y0 minus x0, but I think really we want x0, omega p x0 minus y0, because I think I flipped the sign the wrong way. Okay, now we take this and stick it in here, and we see the 2 omega p's cancel, the minus 1 over I brings the I up, the 2 pi makes this 2 pi to the 4th, dqp, now we have dp0. Remember, dp0 now just goes from minus infinity to plus infinity because it came from a contour integral. So altogether, this thing that we're computing, which is the propagator, df of xy, is then integral d4 p 2 pi to the 4th, yeah, this should be a P0 here, I think. Yeah, it should be a P0. And consequently, I combine this with this term here. And now it's actually worked out. The signs actually have worked out because we want, this is the px minus y in Schwarz's metric.
And so what we get then is e to the I p x minus y divided by what? Well, p0 squared minus omega p squared. Omega p squared is 3 vector p squared plus m squared. So this with 3 vector p squared is just p squared, and then we have minus m squared. So this is just p squared minus m squared plus some epsilon. Okay, and that's the famous formula for the Feynman propagator. And the funny thing is then that the Feynman propagator defined as time-ordered product of the phi of x star, if you want, dagger, phi of y, is the same thing as the as the Feynman propagator of phi of x or phi of y, if phi were just a neutral field. Okay, so that's a long song and dance. Any questions? All right. Let me get a fresh piece of chalk and a few ounces of fluid, because after all, you've got to keep your bowl patients hydrated. Just kidding. It could be a lot more.
Freud says there are no jokes. There's always truth behind what you say. There's meaning behind what you say. There are no jokes.
All right, what did you say? Okay, so all right. Let's first go back and look at what we've got. What we've got here is the mean value in the vacuum of a time-ordered product of something involving momenta and derivatives, phi star of x, phi of y. We can rewrite that in terms of momenta and derivatives acting on the Feynman propagator. So this thing, in other words, time-ordered product, so I'll write the whole bloody thing again. Let me just see what the time is. Yeah, I can think. All right. So clearly, this is just minus P2 mu, P3 nu, minus I, P2 mu, d nu y, minus dx mu, d nu y, plus I, P3 nu, dx mu, all of that acting on df of x and y. All right, and so this S matrix element, Im prime, is E squared, epsilon nu 4 star, epsilon mu 1, integral p4 of x, p4 of y, e to the I, p3 plus p4 y minus I, p1 plus p2 x. And whenever I do one of these calculations from scratch like this, I'm always so happy when the p's line up correctly. So these are the outgoing momenta. And this square bracket, well, let me just write it as square bracket for the moment, times df of x and y. Well, yeah, no, let me write down what df of x and y is here. So it's square bracket acting, of course, on d fourth p, 2 pi to the 4th, e to the I p x minus y I over p squared minus m squared plus I times r. Where bracket is this thing here. Well, let's do as an example d nu y. Well, the derivative on y is going to bring down a minus I p upper nu. Minus I times minus I is minus. Okay. So if you go through all of this, if you do all of them that way, then you get e squared, e4 star nu, e1 nu, integral d4th x, d4th y, e to the I, p3 plus p4y minus I, p1 plus p2 x. And then what you get here is minus p2, p3 mu nu, minus p2 mu p nu, minus p mu p mu, minus p3 nu p mu. And then, of course, the Feynman propagator. And, well, I better not have an integral sign there because this integral sign goes for d4th x, d4th y, d4th p. So we have d4th p, 2 pi to the 4, e to the I p, x minus y, I over p squared minus m squared plus I x. Okay, well, let's integrate, say, over y. If we integrate over y, we see y has, no, let's integrate over x, actually. X has minus p1 plus p2, and then it has plus p. So that gives us delta fourth of p minus p1 minus p2 times 2 pi to the 4th. So the 2 pi to the 4th goes, and we get an overall delta function. That delta function, though, just sets p equal to p1 plus p2, so we can do the d4th p integration. And that cancels the d4th p, the p integration, the 2 pi to the 4th, and it sets p everywhere equal to p1 plus p2. So what we have now is, let me get a decent piece of chalk because I'm down to almost nothing. All right, so this is e squared e mu 4 star e1 mu. And now we've done the x integration, so we just have d4th y. We have e to the I p3 plus p4 y, but there's a y sitting here, and this y has a p, and p is p1 plus p2. And there's a minus sign in front of it, so this is minus p1 minus p2y. So this is the energy, this gives us the energy momentum conserving delta function. Okay, now, all these things are minus signs, and there's an I, So let me pull that out and write it as minus I here. And what we have left then is let me just write it out the way it is. P2 mu, P3 nu, plus P nu mu, P1 plus P2 nu, P1 plus P2 mu, P1 plus P2 nu, plus P3 nu, P1 plus P2 mu. And then all that's divided by P1 plus P2 squared minus m squared. This is plus I epsilon, but the plus I epsilon only matters in loop integrals. We don't know loop integral. All right, so this is the whole thing. And now, finally, the fourth y integration gives us minus I e squared e4 nu star e1 mu 2 pi to the 4 delta 4 is the sum of all the momenta incoming and outgoing to the appropriate signs. And instead of screwing around, let me just tell you that you can rewrite, you can factor this in an appropriate way so that what you finally have here is effectively it's 2p1, p2 plus p1 mu times p3 plus p1 plus p2 mu. It's funny that it comes out that way because, well, there's a P3 that was here all along. Okay. And I don't need the square brackets. And then this is divided by P1 plus P2 squared minus m. All right, so I think that's it. We're finally done. Now, if we strip off the 2 pi to the 4th and the delta function and go back to just m, then the formula is Im equals and minus IE, and this can be written as P2 mu plus P1 plus P2 mu and then I'm going to put epsilon 1 mu epsilon 4 star nu, and notice that these p mu's and nu's, they're contracted with the polarization vectors. I over P1 plus P2 squared minus m squared, and then here minus IE P3 nu plus P1 plus P2 nu. Okay. Well, I don't know why I put parentheses. Okay, now, what we can say is that this part comes from Schwarz's equation 917. This part comes from Schwarz's 917. This is just the Feynman propagator with energy momentum conservation. So in other words, this diagram looks like this. It's
And what was the original thing here? Let's just review. So the photons were 1 and 4, which is obvious from the polarization. Okay, so you take this vertex, you get minus IE, this momentum, and then that momentum. Well, that momentum by momentum conservation is P1 plus P3, P1 plus P2. And then this vertex, well, it's this momentum, that momentum, minus IE, nu, and then these come from the photon field and the initial states, and this is then this electron propagator. So, if you do Feynman diagrams for a living, then you don't go through all the stuff that I went through today. You just say, oh, well, it's this, and you write it down. There may even be some CERN program where you just type in what the initial and final states are, and out comes the LaTeX and the diagrams and everything else. I'm not sure, but anyway, it's conceivable. If not, a couple of years to do that. All right, so that is that calculation. Now I wanted to start another one, but this one I'm going to do simply by using the Feynman rule and not deriving everything of initio or from first principles. And the process that I'm going to be talking about here is called modal scattering. I have no idea how to pronounce MOA, but there it is. By the way, this is E minus goes to E minus. So this will be, modal scattering is electron-electron scattering, elastic electron-electron scattering, and this is electron-electron scattering. And what I was going to mention to you is that Roy Glauber once said to me that when he was at Los Alamos, and he was your age when he was, or even younger, he was at Los Alamos, and Niels Bohr came over for a lecture, and it was almost impossible to understand anything that he said because of his accent. And I think he also had a habit of trailing off in volume the end of the sentence. So, you know, you would say, so this is P2 mu, P3 mu. And it was with a Danish accent, so they just couldn't figure it out. It was also, I heard a story last summer about, I told you this though, didn't I, about the guy at Yale who was Norwegian, famous statistical mechanic person. All right, let me tell you this, Josh. It's sort of tedious. This guy was originally at Brown, and he was brilliant. But they fired him, and he went to Yale. He was in the chemistry department at Yale. He was actually doing physics. He never got his PhD. So there he was doing this brilliant stuff. Somebody remind me what that guy's name is? Norwegian, Yale, maybe 1930s, 1940s, 1950s, maybe early 60s. Anyway, famous statistical mechanics person. Not terrible names. Anyway, he would teach a 2-semester course in Stat Mech in the chemistry department, and the students called it Norwegian 1, Norwegian 2. And he also used a somewhat old-fashioned notation, and in which he used psi for the free energy. And some graduate students were talking sometime during the middle of Norwegian 2. They were studying a group, and they were talking, and one of them said to the other,
I don't know why he uses psi for the free energy. Isn't that weird? And one of the other graduate students said, free energy. I thought it was the wave function. Anyway, so Yale wanted him to get a PhD, and so he wrote up some of his research, which of course was brilliant, and submitted it to the chemistry department. They rejected it. They didn't understand a word of it. Somebody, though, realized how smart this guy was, and so took his thesis to the math department and said, what do you think of this? And they said, holy cow, give him his PhD. And so we got a PhD in math and went on teaching at Yale. Yale very often doesn't treat people well. Apparently Brown doesn't either. Many of the universities don't. What are you going to do? That's another story. Okay, model scattering. So let's now take advantage of all the tricks with Feynman diagrams, and we just write the T-channel amplitude, IMT. And what is the process? Well, it's P1 in, P3 out, photon going across, P2, P4. And I'm going to put the momentum on the photon line like this. Schwartz, I think, has it going backwards, but it doesn't seem to make much sense to have it backwards. All right, so what is this? This is minus IE, because it makes no difference which one you use. P1 plus P3 mu. So that's this diagram, this vertex. Then we have a photon propagator. And what is that? Well, it's minus I over k squared. I'm going to call this k, but of course k is P1 minus P3. There's no m squared because we're talking photon and tree level. So it's minus I, and then this thing is eta mu nu minus 1 minus c k nu over k squared. And then we have this vertex, and well, this vertex is minus IE P2 nu plus P4 nu. So this is again that same equation, what? 9.17 used twice, and then the formula for the photon propagator in this generalized RC gauge and so forth. Okay, well, the first thing is to check that C goes away. Remember I told you that when you do these calculations, you better not have a C in the final state. Well, the reason this goes away is that you have P1 plus P3 mu times, say, K mu. But K mu is P1 minus P3. So this is P1 plus P3, P1 minus P3, and that's 0 just by high school algebra. So this C term goes away. In fact, it's enough for that to go away. Turns out K nu also is 0 on that. So what we're left with is MT is equal to E squared P1 plus P3 mu. Well, we don't even, I mean, if we can just write it as P2 plus P4. It's just the inner product of those two. And it turns out that K, of course, is P1 minus P3 squared. That's just T, the Mandelstam variable. Yes?
I think a lot of us failed high school algebra.
Sorry, say that again.
I think a lot of us failed high school algebra. As you said, by high school algebra, that's 0.
How is that 0? That's what you said.
Oh. Well, these things are on shell. So it's equal to P1 squared minus P3 squared. But that's 0 minus 0. So if it were a massive particle, it would still vanish, but it's a photon, so it's doubly 0. I'll give you a candy in a moment. Okay, so T, of course, is P1 minus P3 squared. All right, let's quickly do IMU. Well, now the diagram is this. P1 coming in, photon across, P2 coming in, selectron going out, P3, and then selectron going out, P4, and now we just do the thing, and it's minus IE, P1 mu plus P4 mu, so that's this vertex. Then we have the super duper propagator, minus I over k squared, eta mu nu minus 1 minus c, k nu over k squared, minus IE, P2 nu plus P3 nu. And that is, of course, this vertex with the P2 and P3. Now, once again, now K, what is K? K is equal to P1 minus P4. And now by high school algebra, the C term goes away. And what we have left is that mu is equal to E squared P1 plus P4 dotted Lorentz-wise into P2 plus P3 over U. And the final answer then, we use equation, let me go over here. We use equation 5.32, which is the same thing as 7.92. And we go to the center of mass frame. D sigma d omega is 1 over 64 pi squared, E center of mass squared, m squared. So we have to add mt plus mu, factor out the I, and so this is just 1 over 64 pi squared. E center of mass, of course, is just S, because that's S is P1 plus P2 squared. So instead of writing it as E center of mass squared, we just write it as S. And then we have mt plus mu squared. Okay, well, it turns out, if we remember that alpha is E squared over 4 pi, with a little arithmetic, we can write that as d sigma d omega is alpha squared over 4s. And now, this is quite amazing, s minus u over t plus s minus t over u squared. That's because this thing here can be written as s minus u, and this one here can be written as s minus t. And that's our final answer. So that is, that's basically all I have to say about that. Let's see, I owe you another candy. Is anybody starving and needs a candy? Okay, any questions?
I'll take a candy.
Question?
No, just your previous statement of is anybody starving and you want a candy, I'll take a candy.
Oh, you're starving?
Sure.
Any other questions? All right, let's turn it off.